Okay. Yeah, it's about time. We should get started. Now, good afternoon, everybody. So we have started our discussion on statistical thermodynamics, or statistical mechanics, and and I'm trying to walk through this using a very simplified version without going into too much details. Okay, so if you find something puzzling you, or you find, well, my argument or my derivation actually should be given some assumptions or more, it's actually with some conditions, and very likely that's true. So you should then ask questions and let me know if there's anything that you are not satisfied yet. Okay. Also, for your review and the study, because the midterm exam actually is coming up quickly, I have uploaded the records of videos of our previous lectures onto YouTube, and provided the link to those videos in our Until Cool web page. So if you check out Until Cool, you can see links to those previous lectures. And some of you have emailed me to ask for those videos, and now I have already processed them and uploaded them to YouTube. I will probably do this more constantly, meaning maybe tomorrow or the day after tomorrow, you will be able to find today's video, okay, on YouTube. I will put it in the same channel, so if you just subscribe to the channel, you can see new videos when it's coming up. Okay, so any questions? Anything? Okay, if not, let me share my iPad. Let's continue. So, so far we have made some discussion on ensemble theory. Okay. And I'm constructing this based on 2 points: statistical theorem, meaning any thermodynamic variable, any thermodynamic property actually observed is an expectation value. It's averaged over many states we call microstates. So any thermodynamic quantity is actually an average. And this average is based on some distribution probability of a certain new microstate. So you need to distinguish between thermodynamic macroscopic state versus microstate. And we further introduce this principle of a priori probabilities. So priori. So you have to make sure I didn't misspell this PRI. You see? Okay. Oh, okay. Probabilities. Which means this probability of nu is actually a function of energy only. So this microscopic state, microstate would have some mechanical energy, and this energy is alone determines this probability of finding a system. And that means everything with the same energy will have the same probability of being found in that state. All microstates with the same energy will have an equal probability. Okay. So given that it's easy to consider an ensemble that with fixed energy, because if energy is fixed, then the probability of finding each microstate will be the same. Okay. And the volume is fixed, number of particles is fixed. And such kind of ensemble is called microcanonical. Microcanonical ensemble. In such ensemble, energy is a fixed value. So one must use a thermodynamic variable entropy S, because S is a natural function of E, V, and N as the major thermodynamic function. And this S can be calculated from a microscopic quantity. That's the whole purpose of statistical mechanics. We want to be able to calculate certain thermodynamic property from microscopic property. And this microscopic property is omega, which is the number of states with this energy. And if we take a natural log of omega and multiply that by a constant, Boltzmann constant, this yields the entropy. This is the Boltzmann's entropy formula. Okay, Boltzmann entropy. And because we know ds, the fundamental equation of thermodynamics, dE is SdT, sorry, TdS, I'm sorry, TdS minus PdV plus mu dN. So we can rearrange a little bit, and we know that now entropy ds equals to 1 over T dE plus pressure divided by temperature dV minus mu T dN. This tells us that one can write down the equation, the probability of S as a function of E, V, N. Then this will be partial S, sorry. This will be partial S, partial E at phase V and N, right? And this will be partial S, partial V at phase E and N. And this will be partial S, partial N at phase E and V. This means once we can calculate S from the number of states, and this number of states will be a function of energy, volume, and the number of particles. And then we can easily calculate temperature, pressure, and chemical potential. And therefore, all kinds of thermodynamic properties can then be derived. So this provides a link between microscopic quantity. This microscopic quantity is the omega here, versus a macroscopic thermodynamic properties. So this is a result for a microcanonical ensemble. Okay. So now this microcanonical ensemble allows us to calculate thermodynamic properties, but it's not very very convenient to use, because in our everyday life, this fixed energy scenario, fixed energy experiments are very difficult to do. Okay. The thing is, once you have perform work on the system, or if you have a heat flow between the system and its environment, energy will change. Delta energy, change of energy is work plus heat, right? First law. Yeah. So in our everyday life, situation, energy goes out and goes into the system all the time. The fixed energy scenario is good for mechanics. In Newtonian mechanics, in quantum mechanics, energy is a conserved quantity, but it's not good for thermodynamics because in thermodynamics, energy is change. Happens all the time. Actually, the whole purpose of thermodynamics is to study how energy exchange affects properties of materials. So fixed energy scenario is not a common, very useful scenario in our everyday life. And more often we need to have the energy change. Okay, change. We need to change the energy. So energy fluctuation, energy change is nature, and we need to study an ensemble that actually is not fixed, and energy is not fixed. Instead, it's more nature in our everyday life that we see a phenomena with fixed temperature. So instead, energy fixed, but the temperature is fixed. Okay, temperature, volume, and the number of particles are fixed. This is more nature in our everyday life. We see isothermal, temperature constant process. We can do that. But to experimentally control a process such that its energy is fixed, this is very difficult to do. Is that okay? So an ensemble with fixed temperature and the volume and number of particles will be more nature to our, or more useful. And this ensemble is called canonical ensemble. This is a canonical ensemble. Okay. And in this canonical ensemble, now energy ensemble is a collection of many states, many microstates. Now we need to consider microstates with different energy. Microstates with different energy. With different energy. But so far we only know how to deal with a fixed energy case. Fixed energy case. So there's a trick here. We need to derive the results, the probabilities. So now microstates with different energy occurs, and we still want to calculate the probability of finding a system in some certain microstate, and this will be some function. More generally, I should write it down as some function, and this function depends on its energy. Okay. So energy of fixed microstate new. But we only know the a priori probabilities. When energy is the same, then the probability of finding the state is the same. If these two microstates have the same energy, then their probability of finding the system in state 1 and state 2 will be the same. This is what we know. This is the a priori principle of a priori probabilities. So the trick here is we need to use the results in microcanonical ensemble to derive the results, the probability in canonical ensemble. And the way we do this is to consider not just a system, but a system plus path. Okay, so we consider for each system, and we say this is system 1, system 1, and there's energy 1. Okay, and its volume and the number of particles are fixed. And there's system 2, E2, volume, number of particles are fixed. System 3. Actually, I should say TVN are fixed. Temperature, given temperature. Temperature, TVN, temperature are fixed. This is all we want. And then we have E new. This TVN are fixed. Many E's. This is what we want to consider. Okay, this is a canonical ensemble. We have many replicas of the same system. Each system will have a different energy because now energy can change, but their temperature, volume, and the number of particles are the same. And to kind of make this microcanonical ensemble, we actually can attach to each system, to each replica of the instance of the system here, we attach a bath to it. So there's a bath. So this is a bath attached to it. And this E1B. And this is, we attach a bath to it. So this is second system and this bath. B. E. Bath. So if we consider system only, this is canonical, C-A-N-O, canonical. But if we intentionally make total energy equals to system energy plus bath energy for all the microstates, regardless of the microstates, we consider its total energy is fixed. Okay. And this is quite natural physically because you consider in the universe, the total energy is conserved. So the system is in contact with an environment all the time. If the energy will fluctuate, the energy has to come from somewhere, from its environment. So energy flow between the system to the environment and from the environment to the system will make the energy of the system change. But the total energy, the energy of the universe, remain the same. Okay? So total energy is a constant. System energy and the bath energy, the partition of total energy can change. That's our everyday life. That's a real scenario, physical scenario here. And physically, this energy of the bath must be much greater than the energy of the system. So compared to the environment, compared to the universe, the size of a system is very small. Okay. Otherwise, it wouldn't be a heat bath. Heat bath means we put a system into this environment, then whatever the system change, the environment remains the same. Okay. Just like independent of my temperature, the temperature of the Earth will not change because the size of the system versus the Earth, the environment is just too different. The bath has enormous more degrees of freedom. So the system energy flow into the bath, the temperature of the bath will not change. And actually, this temperature is defined by the bath temperature, not by the system's temperature. So far, okay? Okay. So now, because the total energy is the same, so each system plus best system state would have the same probability to occur. So if we consider system plus system only is a canonical ensemble, but system plus best states, this became a microcanonical. So for each system energy, for each microstate, the energy, its energy is E nu. We know that the best energy will be this total energy. Let's call it E0 minus E nu. Okay. Let's call this total energy E0. So number of system states for nu, if we call this omega E nu, and this is for system. This is for system. So then I'll put a subscript omega s here. For simplicity, here we are not going to consider system with degeneracies. But if there is degeneracy, this will be a degeneracy number. Okay, so this is actually in quantum mechanics or in statistical mechanics. Sometimes we use G nu to denote. Okay, so this is a degeneracy.
Sorry, Professor.
So yes.
I think I missed the term of energy B equal to E0 subtract E. Yeah,
No
can
problem.
you explain again?
Because the total energy, system plus bus, the total system, the total energy will be the system energy plus bus energy, right? Right?
Yes.
Let's call this total energy E naught, E0. Let's call this total energy E0. So it's just the total energy. And we assume this total energy is fixed because in the universe, the total energy of the universe is fixed.
Mm-hmm.
It's some fixed value. Okay. Independent of which system state, the total energy remains the same. Is that okay? So if this is the case, then the best energy will be this total energy minus system energy. So this is this equation. Is that okay?
Okay.
Then next we want to discuss the dependence of a number of states with energy. So we first consider number of system states. And number of system state for a given energy actually is called the degeneracy of that microstate. Okay, so in in quantum mechanics, you solve the Schrödinger equation, then you can find at some given energy how many states will have the same energy. For in hydrogen, for example, hydrogen atom, for example, you have n equals 2. There are 4 states that will have the same energy. This is degeneracy. But for simplicity, we are not going to use this G. We'll assume non-degenerate states. So for each microstate, we can see only one state. This is still very general. It means we do not consider degeneracy. We just consider degenerate state individually. And you have exactly the same result. Okay. So number of states, this is solved. We assume it's 1 because we consider each microstate non-degenerate. We use non-degenerate rule to consider microstates. The problem is actually the number of bath states. Okay, the number of bath states. And the number of bath states will be some bath number of state function and consider this energy, EB, bath energy. Bath energy. And this will be omega B. We know EB actually is determined by the energy of the system. So total energy minus E mu. So the key here is actually this statement. This is a statement regarding a very simple physical reality. That is, whenever the system fluctuates in energy, when the system has different energy, then this additional energy or this required energy must be must be due to this change in energy must be due to energy exchange with its environment. So the bath will be changed. Okay, will have a different energy, and different energy. The best states with different energy will have a different number of states. Okay, so the best number of states is related to the energy of the system. If the system energy is higher, meaning the best energy is lower, so it's E naught minus E nu. If E nu is higher, then the best energy is lower, then the number of states accessible for the best will be smaller. But the higher the energy, the number of states, higher energy will leads to higher number of states. Okay, because if you have more energy, you can go to more states. More energy, is more likely that you can go to excited states. So the state space.
Sorry. So that mean high path energy mean high path state, and high system energy mean high system state, right?
I'm talking about number of states. Okay, so
I mean it is correct for both of number of system state and path.
So the following statement is true all the time. It with as the energy increases, the number of accessible states increases. Is that okay?
Yeah.
So whenever energy increases, then this number of states accessible with this energy increases. This is true. This must be true. Okay. If this is not true, you will have a negative entropy or negative temperature. Okay, let's go back to here. So actually, number of best states are determined by, or is related to the energy of the system. It depends on which microstate the system is in. Okay. And the number of total states the real omega actually will be the number of system state times the number of best states. And that, like I said, I consider non-degenerate system states. So each microstate, each system microstate has a single state. There is no degeneracy. So this is 1. And the best state is determined by this energy difference. So this equation tells us that the total number of states of the total system. Now this total system is a microcanonical ensemble. So now the total each state have the same probability. So if we have a more number of states, the probability increases. The probability is now proportional. In a microcanonical ensemble, the probability is proportional to the number of states. What I'm saying is, this is an instance of a microcanonical ensemble, system plus BAS. This is another microcanonical ensemble, system plus BAS. Then the number of states here is this E0 minus E1. This system energy determines the number of states. This one, number of states, is determined by E0 minus E2. So the system energy determines the total number of states because system energy affects the energy of the BAS. And the BAS number of states will vary. So in this case, all the system, microstate 1, microstate 2, microstate 3, is a single microstate. But given this energy, the BAS would have many, many different states. So the number of BAS states determines the total states. So this is actually depends on rho B, BAS number of states. And the probability of finding system in E1 now is proportional to this number of states because each such instance will have the same probability. So then you count how many of them are there. And that's proportional to the probability of finding your system in that particular microstate, system microstate. Okay. So what I was saying is that your probability of this system in this microstate actually is proportional to the number of total states. System times BAS. But system here is only 1. We consider non-degenerate case. So everything is actually determined by the BAS number of states at this given energy. Okay. So now let's estimate. Omega B E minus E nu, or E0, E naught minus E nu. Because E naught is a number E naught much greater than E nu, so we expand natural log omega B around E naught. Why natural log? Because number of states actually is a large number that grows exponentially. Okay. Whenever you have many degrees of freedom, you add more degrees of freedom, you add more energy, the number of states grows exponentially. grows exponentially. So you need to take natural log of it to control the exponential growth and then do the expansion. Otherwise, you are making expansion around a large number, and that expansion would not be accurate. Okay, because so this is essentially this is because omega b is a large number. You do not do expansion on a large number. It grows exponentially. The expansion will not converge easily. But in that case, we know how to deal with it because you can then take natural log or take whatever log. But here, of course, we choose natural log. You take log, and when you take log, a large number becomes a small number, and then this expansion can then be converged. Okay, so this is a trick that's very widely used in statistics. Instead of taking average on the number itself, we take average after natural log. Okay, so this is what we will do. So let's take the expansion. So the natural log omega, natural log omega e minus e nu would be first natural log omega e 0, yeah. And then you take the first derivative of this natural log with respect to e, right? So the Taylor expansion first term will be partial natural log omega partial e at e0 at this point. Next point. Then you times the difference here is minus EV, minus E nu. Sorry, this is the first term. And higher order term we neglect. So we expand natural log omega b to the first order. And you see that this became natural log omega E0 minus partial natural log omega partial E at fixed E0. And also fixed V and N, of course. Everything here we consider is in fixed V and N. So I will write this more specifically here. And according to our next lecture, entropy is KB. Microcanonical ensemble entropy is KB natural log omega. Right? So partial natural log omega, partial E, fixed V and N. This is not, so it should be fixed V and N evaluated. So I shouldn't write this exactly. Evaluated at E equals to E0. So this is evaluated. V and N evaluated with E equals to E0. That's more, that's better. So this became 1 over KB times partial S partial E. V and N. So we learn about this. And partial S partial E is 1 over T. This is how we define temperature. So this is actually 1 over kBT. And in statistical mechanics, we are more inclined to use inverse temperature, beta. This is defined as beta. So beta equals to 1 over kBT is the inverse temperature. So what I was saying is this is inverse temperature. This is beta. So this natural log omega E0 minus beta E nu. This is natural log omega B. This is all depend on B state, best state. So this beta, this temperature became the temperature of the bath and bath environment, temperature of the environment. And that's how temperature is being defined, right? And this tells us that omega B is 0 minus E nu, so is proportional. This term is a constant. It's just a proportional. It's just the proportionality constant of the equation. We write proportional, then what's this second term, linear term, determines this result. And this is natural log, so this is exponential minus beta E nu. So the energy of the system determines the number of bath environment states. When energy increases, energy of a system increases, the energy of the environment decreases. And this decrease in energy would reduce the number of states exponentially. This is a key here. And this is according to the priority probability, we know that the probability of finding the system at this microstate is then proportional to this best number of best states at this system energy, and then it's proportional to exponential minus beta E nu. And what is this? This is a well-known Boltzmann distribution. So because in the universe the energy is conserved, so if the system energy fluctuates, the lower the system energy, the higher the environment energy, and then there are many more environmental the best states, number of states, and this leads to more likelihood of finding system in a low energy state, because if the system have low energy, then the bath will have more energy and more bath states, entropy will increase. Okay. So we derived Boltzmann distribution, and we know that for canonical ensemble, the probability is proportional to, and we can rewrite this as an equation. We can say, so the probability of finding a system in the new microstate will be some normalization constant and minus beta E nu. And this normalization constant will be sum over all the microstates nu exponential minus beta E nu. So this Q is called canonical partition. Not only is a normalization constant in this probability, it's also a generating function for all sorts of thermodynamic properties, and we will see this very soon when we come back. Okay, so I'll stop here. Think about it. And we don't need to take a 10 minutes break. We will take a 5 minutes break. So according to my computer now, it's 2:05, 5 past 2, and we will return at 2:10. Okay, 10 past 2. Think about it, and let me know if you have any questions when we come back. Okay. So any questions? Okay.
Professor,
So
homework
please.
in homework 2, homework 2, question 6 is the exercise in, I think it's exercise in book. So which books?
Chandler's book, we talk about this in our first day of the lecture. So if you go download take a look at the syllabus on until cool, you see our textbook is Chandler's this.
Okay.
Take a look, okay?
Okay.
Okay. Modern statistical mechanics.
Yeah, I just make sure.
So anything else? So this canonical partition function Q actually is not just a normalization constant. It's actually a generating function, Generating function of thermodynamic variables or thermodynamic properties. How come? I'll use an example to illustrate this. As long as Q is known, then let's calculate this function. We take the natural log of Q and then take derivative with respect to the inverse temperature beta Vn. Okay. And what is this? What is this? Because Q is this sum over all the exponential. So let's plug that definition in there. This natural log sum over new exponential. Let's not do this so fast. Sorry. Let's explain. Let's get rid of this natural log first. So this partial natural log partial beta use applying chain rule. Okay. So this became minus 1 over Q times partial Q partial beta Vn. This is just chain rule. Right? And then Q is this. So when you take derivative with respect to beta, you have a minus E nu. So this became minus 1 over Q times, now we have a sum of all new states, but you have then minus E nu times exponential remain the same, so exponential minus beta E nu. Okay. And this minus sign and this minus sign goes away. Okay. And this became, move this Q here. Okay. So exponential minus beta E nu divided by Q is the probability. So this is sum of all states, the energy of that state, and the probability of finding the system in that state. And what is this? This is the expectation value of energy. This is expectation value of energy. And all the thermodynamic variables, thermodynamic functions are in fact expectation values. So this is thermodynamic internal energy. So to calculate energy, you take the natural log of Q, then take the derivative with respect to beta and plus, and then this minus sign, you get energy. So how we calculate energy? Furthermore, because now energy is minus partial natural log Q partial beta constant Vn, and a simple mathematics tells us, so this is actually no need to mathematics. Beta is 1 over kBt, so this became minus kb times partial natural log Q partial 1 over T, the first Vn. And then we know, furthermore, from thermodynamics, this is from thermodynamics, we know that energy is partial Helmholtz free energy divided by temperature. This function, partial 1 over temperature. So go prove this. This is a quick exercise. You should be able to give a proof for this. Right? Try this as an exercise. And then this is according to this thermodynamic identity. And this identity we derive from statistical mechanics. There's this partition function in there. We compare this two. We know that partial A over T, partial 1 over T, Vn must equals to minus Kv, partial nature of Q, partial 1 over T, Vn. And this tells us this function. This is true for all equilibrium states, for all thermodynamic systems. So this function and this function must be the same. There could be some constant of integration. So they can be differed by a constant. But this constant is not does not affect all the calculation in the change in this free energy. So we can just eliminate this constant. Just like we redefine the zero energy point to make this constant go away. Okay, so of course this must be included. This means A over A is the Helmholtz free energy. Helmholtz free energy divided by temperature. This function mass equals to minus Kv nature Q. So Helmholtz free energy can be calculated from partition function, canonical partition function. Minus kVt nature of Q is the Helmholtz free energy. Like I said, this is derivative, so they can differ by some constant C, but we can just shift energy 0 point to get rid of this constant. So it's we do not need to consider this. Okay. And now we know that if we know the Helmholtz free energy, we can calculate all sorts of thermodynamic variables. Again, now we are in the fixed temperature TVN. So in this condition, the nature variable with nature variable T, V, and N as the nature variables, the function is the Helmholtz free energy. So it's nature that we can calculate nature Helmholtz free energy from partition function. And the equation total derivative of Helmholtz free energy is minus S dt minus P dV plus mu dN. So I'm not going to write the equation down, but clearly we can now calculate entropy, pressure, chemical potential from derivative of Helmholtz free energy with respect to T and V and N respectively, right? And this A can be calculated from canonical partition function. So once you can calculate canonical partition function, Q will be a function of the T, V, N. Then you can calculate all sorts of all sorts of thermodynamic properties, right? So this covers all the basic principles of statistical mechanics. The procedure that we use in statistical mechanics is we given a system condition, the Hamiltonian of a system, we calculate partition function. And how do we calculate partition function? Now we go back to the definition of a partition function, this equation. If you know all the system microstates, and sum over this exponential factor, you get the partition function. So we need to know all the energy. And normally we consider those are eigenstates. If starting from quantum mechanics, you solve this time-dependent Schrödinger equation, you get many eigenstates, and you know all the energy of the eigenstates, right? And then you sum over all the states, you get this partition function. So as long as you can solve time-independent Schrödinger equation to obtain all the energy with the state, what is this? This is a spectrum of the system. Energy spectrum of the system. Normally you get this from solving time-dependent Schrödinger equation, and you can calculate partition function. And once you calculated the partition function, you calculate Helmholtz free energy, and then all sorts of thermodynamic properties. Done. We provide a very clear and useful link between microscopic quantum mechanics, or for that matter, Newtonian mechanics also, with macroscopic thermodynamic properties. To deal with classical Newtonian system, there's a caveat of how do we count number of states, but we will go back to that later. Okay, we will provide a link between classical statistical mechanics and quantum statistical mechanics. For quantum system, it's actually easier because quantum system has discrete energy spectrum. Quantum system has discrete energy spectrum. So this microstates, definition of microstates, and the energy of microstates are defined naturally in quantum mechanics. So this is easier in quantum mechanics, but it's a little bit trickier in classical mechanics. But we will deal with that later. The problem is in classical mechanics, there's no discrete states. So this summation cannot be performed in classical mechanics. And we need to change this summation into integrals, okay, over continuous position and momentum variables. But that's a topic we will cover later. Okay. So this prescription of using microcanonical ensemble already allows us to deal with many problems. But sometimes microcanonical ensemble is not the most convenient ensemble. Okay. Because in microcanonical ensemble, we assume the number of particles are the same, remain constant. But in many scenarios, especially scenario important for chemists, chemical reaction, chemical equilibrium, for example, number of particles, because in chemical equilibrium, A is in equilibrium with B, then number of A and number of B will change. Dynamically, A became B, B became A. Right. So in that case, you will need to consider an ensemble without fixing the number of particles. And that ensemble is called grand canonical ensemble. So in grand canonical ensemble, the number of particles can change. So I will write it down, but I'm not going to discuss grand canonical, G-I-N-D, G-R-A-N-D, canonical ensemble. It fixed only T and V. Sometimes T and P also can also be dealt with. Temperature, pressure, temperature, volume, but number of particles cannot change. And in that case, In that case, there's you need to introduce the when n can change here. When n can change, you need to introduce this chemical potential term into your probability function. So you have a different statistics. But I'm not going to go into details for grand canonical ensemble. I have uploaded a brief note on grand canonical ensemble and how it's been applied to statistical mechanics to NTU Cool. Interested students can go take a look. It's optional. It's not required. Because right away, I'm going to tell you that all the ensembles are the same. If we can treat the problem with microcanonical ensemble, you can also treat it with canonical ensemble. If we can deal with as canonical ensemble, maybe it's more complicated, but it's also can be done by using a microcanonical ensemble because microcanonical, grand canonical, they are all the same. With the condition that if it's in the thermodynamic limit, in the thermal. So this is a very important issue, and it provides a microscopic statistical explanation on how thermodynamic limit emerges. So I'm going to talk about thermodynamic limit. The idea is this. Let's consider a canonical ensemble. And because canonical ensemble, the energy can be a function of time. So energy change is a function of time. So if you look at the system, its energy should fluctuate. And you actually have some average energy. This is defined as the internal energy of the system. But then because it fluctuates, so anything that's not in a fixed value, but there's a range of a fluctuation, we will use standard deviation or variance to measure it, right? So this width of the distribution is related to some standard deviation. And standard deviation was square root of by definition, E square average minus E average square. So there is some variation. Normally, if it's a Gaussian distribution, we use standard deviation to measure this variation. And this variation gives rise to this different value of energy. So energy can change. So let's estimate E versus this sigma. More precisely, we want to know this ratio. This is the relative amplitude of the fluctuation compared to the size, the energy, compared to the energy, the value of energy. What I'm going to prove here is this ratio is extremely small. It's so small that we might just consider this as 0 as well. 0. And the condition that this value became very small, and it's very small, so this sigma, this variation would not be able to be detected by any experiment, any a microscopic experiment. The requirement is that the system is with a large number of degrees of freedom, and this is a requirement for thermodynamic limit, because in this limit that you do not see the fluctuation. So all the thermodynamic variables has a very well defined equilibrium fixed value. Okay, if you look at if you measure the average energy of a cup of water, average kinetic energy of a cup of water, you will not be able to see any this kind of wiggling of energy in time. It's all steady, the same value within with all likelihood within experimental uncertainties. Yeah. So let's do this calculation, and this requires us to calculate. We already calculated this average energy. We already done it. So what we need is this E square. So let's estimate E square. And because this is sum over all the microstate, by definition, value square times probability, value square, G square. And plug in the probability in terms of the partition function and Boltzmann distribution minus beta E nu square. Okay. And this will be easy to verify that partial square Q partial beta square at this million. It's easy to verify this because Q is this summation exponential minus beta E nu. So partial beta minus E nu, partial beta again. So take second derivative, you have E nu square, right? And this is actually why it's called generating function. Okay, come back here. Okay. And now realize that natural log Q is minus beta A. This by definition, A is minus KB natural log Q. So we have this equality, natural log for natural log Q, natural log Q. So partial square natural log Q, partial beta square. This would be, let's take the first derivative first. Partial natural log Q partial beta would be 1 over Q partial Q partial beta, right? And then we take the derivative again. But now you have a 2, Q depends on beta. Partial Q partial beta also depends on beta. So to do this derivative, you need to take derivative of this first term and second term remain the same. So this will be partial beta 1 over Q, 1 over Q. I'll do it slowly. Plus 1 over Q, partial square Q, partial beta square. Okay. And you see, this is what we see here. This is what we see here. And Q, square, Q, this is, so this is E square. And here, natural Q is minus beta A. So this equals to partial square, partial beta, partial beta square, minus beta A. Minus beta A. I want to come up with some average energy square. Average energy square. Should be this. So this is Q square minus Q square times partial Q partial beta. Oh yeah, yes. So this is minus 1 over Q, then Q partial beta. And this is average energy, partial nature of Q, partial beta. Okay, I should give where I want to go first. The identity I want to prove is this E squared should be partial square nature of Q, partial beta square at fixed V and N plus average E square. Okay, this is actually what I should have obtained. And how this identity came about, let me see. One way to prove this is actually, let's take derivative of this. So that's what I just did. So partial square nature of Q partial beta square would be partial beta. I'll do it again. Partial nature of Q 1 over Q partial Q partial beta. And then you have partial 1 over Q partial beta. Oh, I forgot to multiply this partial Q partial beta back. Oh, I'm sorry. So this is partial beta 1 over Q. Nice. The first term is partial Q partial beta. Yeah, I got it. The second term is 1 over Q partial square Q partial beta square, right? And this equals to this. So equals to this. Now what is this? This tells us is 1 over q is 1 over q minus 1q squared times partial q partial beta. But you have a 2 partial q partial beta squared. And we know 1 over q partial beta is natural log q partial beta, right? And partial natural log q partial beta, partial natural log q partial beta give us minus energy. So this is minus energy. But it's a square of this to this such terms. So this term became this plus. Now this is E squared. Average. Yeah. And this is E average then square and minus sign. So this is minus E average square. Yes. Square. And what is this? This is a variance, E square. Yes. So be careful about the derivation. Yeah. So even previously I forgot. When you take the derivative, you see you take derivative here. This term have to multiply back here. So you square here. Yeah. So I will use this. This is the standard deviation. Oh, actually, this is variance, average of square, second moment minus first moment average square. This is variance. So this variance equals to partial square natural log q partial beta square. So let's evaluate this. I will call this delta E square. So delta E square average is defined as E square minus E square variance. And this variance, according to what I just showed, is partial square natural q partial beta square at fixed V and N. Now I want to use this connection to thermodynamics because later on I want to make argument relate this to thermodynamics. This is actually a microscopic quantity. This fluctuation, this variance is a microscopic quantity from statistical mechanics. But this variance can be determined from macroscopic thermodynamic properties. How? Because natural log Q and Helmholtz energy have this particular relationship. So natural log Q actually will be minus beta A. If we plug it in this here, we will have partial beta. Forget about V and N first. Actually, not forget, it's implicitly we already assume that. I just don't want to write it all the time. Okay. So natural log Q is minus beta A, partial beta. This is what we want to evaluate. And minus sign all the way out here. And we have a partial. I'll write it down, okay? This will be partial. Beta is 1 over kBt. So we have a 1 over kb for outside. And beta here, there's also 1 over kBt. So 1 over kb can be pulled outside, and we have a partial t This beta, we change this to temperature T. And inside here, we change it to A divided by T. A divided by T. Partial. A over T. Partial. Sorry, 1 over T. Not T. 1 over T. Minus sign goes here. And I told you that it would be a good practice to show that this is internal energy. You can show this by some thermodynamic equations, thermodynamic identities. This is a thermodynamic identity. So this is energy, internal energy, average energy. This is average energy. Thermodynamic average energy. And this will be minus. I'll pull this 1 over kV outside first. So this kV times partial 1 over T times partial E. V and M first. It seems complicated. That's because I'm working slowly. Yeah, actually, it's quite straightforward. It just you need to be careful about this mathematics here. Yeah. So now in the end, you can you will show that. No, not I will show that. But I will write it down. This is KB partial E partial T and then partial T partial 1 over T. Chain rule. This is a trick because then we know that partial 1 over T partial T will be T squared minus 1. This is easy to see. So inverse of this partial T partial 1 over T will be minus T squared. So this term is minus T squared. Minus T squared. And this term at a constant volume, when temperature change, constant volume, there's no PV work. There's no work related. So when you increase the temperature, the amount of energy increases is the heat capacity at constant volume. So this is CV. So I show that this variance in energy, in change in energy, is Kb temperature square, this minus sign goes away, times the capacity at constant volume. So our standard deviation, our fluctuation in energy, goes like square root of kV T squared CV. And what we set out to do, this ratio, will be your total energy and then square root of kV, this constant CV times T. So as temperature increases, this ratio increases linearly. That is in accordance with our intuition. At higher temperature, this fluctuation will be larger. But the key is the ratio here. They have a different scaling with respect to the size of the system. So if system has n particles, number n particles, we know that sigma E, Kv is a constant, T is intensive, Cv is extensive. So do it slowly. So we know Cv goes like N. And your energy also goes like N. But your fluctuation in energy goes like square root of N because it's square root Cv. So your fluctuation in energy divided by energy, total energy, goes like 1 over square root of N. This means if you measured some average energy, you measure some average energy, then the fluctuation of energy, N must be greater than 1, a large number. The fluctuation energy will be much smaller than your energy. But how smaller? How much smaller? Let's estimate this. So N, how many particles normally we have? And like 10 to the 23. So this ratio, go like, let's forget about this 23, let's say 22. 22, make it easier. Let's not consider 23, 22, 22. And this will be 10 to the 11. But 10 to the 11 is a very, very large number. Okay. It's so large that you cannot possibly see it in our everyday experiments. What I'm saying is this kind of fluctuation curve that I drew previously, this is unphysical, this is wrong, this is incorrect. Because this change, this sigma, and this is this energy, sigma over E must goes like 10 to, oh sorry, this is 10 to the minus 11, not 11. 11 is a large number. It's minus 11, it's much smaller. Minus 11. So let's say if this must be 10 to the minus 11 times of this total energy, then it's not just a flat line, it's this most flattened curve that I can draw. It's impossible. You use a ruler to draw it. It's even more than that. Agree? If I draw this line using a ruler, and nowadays, if you enhance and enhance, you see the line width will still fluctuate, right? Still change. And this change will be much greater than 10 to the minus 11. So there is no fluctuation at all. What I'm trying to say is this change in energy, this energy fluctuation, can be seen. So we have a well-defined thermodynamic quantities. So all the thermodynamic quantity, all the thermodynamic variable, thermodynamic properties remain constant. You cannot see the fluctuation. And since you cannot see the fluctuation is so small, you might just ignore it as well. So Michael's canonical ensemble, fixed energy, fixed average energy, and the canonical ensemble, fixed temperature, became the same. So as long as you can fix the temperature of the system, the internal energy of the system will also be fixed because the fluctuation, you allow energy to flow between your system and the environment, but the fluctuation, the flow will be so small that you cannot possibly observe it. You just cannot see it. So effectively, regardless of what kind of ensemble you choose to work with, in the end, you get the same results. In our everyday life, we only see the average because the fluctuations for macroscopic systems are so small. Impossible to see it. And this is the requirement for thermodynamic limit. Now consider if the number of particles is much smaller. For example, not in the 10 to the 23, but in the 10 to the 12 level, then the square root of that is 10 to the 6. 10 to the minus 6, 1 in 1 million. That's something we can measure in our everyday life easily. Okay? 1 per million. Okay, we can measure that. So if you consider smaller and smaller system, and nowadays when you are studying narrow scale systems or system in mesoscopic world, this thermodynamic limit became fuzzy, and this fluctuation must be taken into account. And not all thermodynamic rule would be hold in that scenario. So for thermodynamics to apply, for equilibrium to be able to be established, a macroscopic system with an enormous number of degrees of freedom is required. Okay. Any questions? So if no questions, then let's go to let's go to our class log. Okay, and I'll show you. We have a few minutes left, and I want you to kind of work on it by yourself a little bit. So I'll share my screen and let's take a look at this class log I posted today. And if you scroll down there, or someone already posted the answer here. Oh, it's fine. I want you to practice on 2 proofs. Okay, I think there's no need to go to group discussions. So originally, this should be processed like we'll go to group discussion and everybody write down your answer. You compare your answer with your group members, and so that your group members you can teach each other what's correct, and then post your final answer here. Okay, but I will just leave it here, and for all of you, each of you to work on it and post your answers here, and you can see other people's, you can see other answers. Okay, and you can take a look and see. Don't just copy it, please. Do not just copy others' answers. Try to think about it and come up with your own answer. Okay, and take a picture, take a photo, and upload your answer up here. So 2 questions, actually 2 proofs that we talk about in this lecture. One is this very simple proof of a partial natural log omega partial E is 1 over KBT is beta. This is used when we derive this Boltzmann distribution. Okay. The second one, regards this energy equals to partial A over T, partial 1 over T, this is equality. Okay. Upload this one also. Let's upload this one also. This one also. Okay. so that we can see each other's answers and get a good ideas of how this is done. It's thermodynamics, so there can be multiple equivalently valid proofs. So just, but you need to go through it by yourself. Yeah, it's very important. So I'll leave these 2 questions here for you to work on it. This is optional. This is not a quiz. And this is not going to go against your final grade, okay? But this will be evaluated on the basis of class participation. Normally, I use those records as a source to give bonus points. So if you participate more in class, you ask more questions, it's very likely that you will get bonus points in your final score. That's what I normally do. Okay. Yeah. So it's optional. It's not necessary that every one of you must post your answer here, but it's encouraged. Okay. Any other questions?
Professor, I want to ask about the format of the midterm.
Format of what? Can you say that again?
Format of the midterm.
Format of the
期中考.
What? Oh, midterm exam. I suppose we will. So let me check it. Our scheduled midterm is October 26th. Is that right?
Yes.
Yes. So I suppose we will have everybody come to school, come to university. We will have a paper test for the midterm exam.
I see. Thank you, Professor.
Okay. And the plan now is I will keep using online meeting room to teach this class until after the midterm. So the plan I have right now is we will resume our class in person after midterm exam. Okay, that's my plan. That's my plan. But before midterm, we will continue in this online version.
Oh, I see. Thank you, Professor.
Okay. Anything else? Okay, if not, I will stop here. I will close this meeting room, but you can still work on your proof and post your answer to the Google class log. Okay, it will remain open. Okay, and I encourage all of you to give it a try.
Professor, you can keep this class log until Thursday.
Yes. Yeah, no problem. No problem. Yeah.
Oh,
and normally that's what I did. Because I normally edit this class log just before the class. Okay.
I see. Thank you, Professor.
No problem. Okay, so see you on Thursday.